Okay, hello everyone. Okay, in this video, I'm going to talk about the beam deflection calculation or elastic curve calculation. Okay, on the beam. Okay. So this PowerPoint I list the calculation procedure. Okay, and I think just four steps. Okay. Because the problem in this type of problem, most of the time the beam is placed on a support. Okay. So first of all, okay, we need to use the rigid body equilibrium to calculate the reaction force or reaction moment from the support. And then after you calculate this reaction force and reaction moment from the support, and then you will have the complete external loading and external moment acting on this beam. And then you can use it, and then you can write down your loading function. But for the loading function, you have to represent the loading function by discontinuity function. And after you write down the loading function and then integrate the loading function twice, okay, you get the moment function. And after you get the moment function and plug the moment function in the final differential equation with the boundary condition, you can solve the V. You can nu of V. Okay, I'm not sure. It's solve the V. Okay, or nu. Okay, you can solve the nu. Okay, or mu. Oh, nu. Okay, so solve the nu. Okay, and nu is the deflection or elastic curve of the beam. Okay, so yeah, I won't say the calculation is very difficult, but just it's take time, take time, and then there's a tiny detail you need to notice. Okay. Okay, first of all, let's use this the example. Okay, this example is a cantilever fixed on a wall, and this wall is a fixed support. And then we will have apply loading and apply moment acting on this beam. Okay, here is a distributed load, and here is a concentrated moment. Here is a concentrated loading. Okay, first of all, find the elastic curve, and then I add another question. Suppose the elastic modulus of the beam is 200 gigapascal, and the moment of inertia of the cross-section area of the beam is 65 and 10 to the power 6 mm power 4, and find the displacement at x equal to 3 and x equal to 8. Okay, because the calculation procedure yeah, is very long, so I don't have I don't think there's not much space here. So I use another panel here. Okay, so okay, here's another panel. Okay. Okay, so let's first of all we have to use a rigid body equilibrium to calculate the reaction force and reaction moment from the support. Okay, so let's start with it. Okay, let's start it. So first of all, you draw the free body diagram of the beam. Okay, and then at point A, we have because it's fixed support, so we have reaction moment. Okay, and also reaction force AX and AY. Okay, so that's the first step. Okay, and then we have to use rigid body equilibrium to solve the MA, AX, and AY. Again, don't forget it. Okay. And now, so when we do the rigid body equilibrium, we have to do some simplification of the force. Okay, so here is a uniform distributed load. Okay, so what's the resultant force? Okay, the resultant force is the area under the curve. So it's A times 5, so it's 40. And where's the position of the resultant force? Because this is rectangular, right? So it's the center is here, 2.5. So maybe it's here, and its point down is 40 kilonewton, and here is 2.5. Okay, and here at x equal to 5, there is a localized or concentrated moment. It's 50 kilonewton times meter, and at the end of this rod, there is a local concentrated load in 12 kilonewton. Okay, so let's read the free body diagram of this beam. Okay, first of all, rigid body equilibrium. So this two-dimensional problem. Okay, the x component, the net force in x component must be 0. Okay, so in this system, we only have the ax equal to 0. Okay, okay, that's very trivial. Okay, so the next thing is the net force of the y component must be 0. Okay, so at the position A, we have ay. Okay, and I assume it's okay. My notation is okay. I mean, I just the list notation. We assume point up is positive, and counterclockwise is positive. Mm-hmm. Okay, so next, okay, AY, let me see, AY here, and we have, here is 40 kilonewton, but it's point down, so it's minus 40. Then don't forget the units kilonewton. And this moment we leave, we just right now we just ignore it, and there's 12 kilonewton at the end, so minus 12. Okay, it's point down, so it's negative. So we have the AY is equal to 52. Okay, it's the units kilonewton. Okay, and also the overall moment, because statics, the summation m must be 0. Okay, the total moment must be 0. Okay, and then yeah, maybe here I didn't make a very good notation here. So okay, so okay, here we have a moment at the point position A, so it's MA, and we have another moment is 50 kilonewton. Okay. Sorry. Sorry. I should I should mention this first. Here is 40 kilonewton point down. Okay, and then it's this force will create the moment, and it's counterclockwise or clockwise. So this force is point down, and the reference point is A. So it will become a clockwise. So clockwise is negative. So minus 40 times 2.5. And the next one is also 50 kilonewton times meter. It's also clockwise. Okay, so it's minus 50. And the next one is 12 kilonewton at the end. Okay, so this force is this force is point down, and the reference point is here. So it will create a clockwise moment. Okay, clockwise. Okay, so it's 12. So it's negative, it's 12, and times what's the moment arm or lever arm? The moment arm is 9. Okay, so be careful of this. 0.9. Okay, and then equal to 0. So we will have the moment at the A position. A is and 258. Okay, kilonewton and times meter. Don't forget the unit is kilonewton times meter. Okay, so after you write down, after you finish the rigid body equilibrium and calculate all the support reaction, or all the reaction from the support, all the reaction moment from the support, and then you have complete picture for the loading of the beam. So the next step, we have to write down the WX. Okay, we have next step is write down WX. Okay, let me move. Okay, so WX. Yeah, we change the color. Okay, WX. Okay, let me write down the loading function. Okay, the loading function, you have to start from the origin. Okay, so the origin, what do we have? Okay, at the origin position A, we have the AY, right? We have AY. Okay, point up, and we have MA moment. We have moment and reaction force AY, and the AY is point up, and this is a concentrated loading. Okay, if we want to represent the concentrated loading by this continuity function, how to represent that? Okay, first of all, it's 52, and it's positive. Going up is positive. Okay, and then the power of the concentrated load. Okay, is what? -2 or -1? Any idea? So and it's at position 0. Okay, we set the origin at the point A. So it's minus 0. And what's power? The power is minus 1. Okay, don't forget it. In the position A, we also have the concentrated moment. The concentrated moment, MA. The concentrated moment, okay, is 258 kilonewton times meter. And the concentrated moment, the power is, okay, its position is also at 0, and its power is minus 2. Okay, and here we have to notice to be a caution, because I say just like we did in the shear moment diagram, the moment here we want the internal moment, okay, and the moment we calculate at the support is the external moment. So, but when we do the calculation, we want the internal moment. So we have to use the minus sign in front of the MA to get the internal moment. Okay, don't forget it. Don't forget. Okay, so that's we have the reaction force and reaction moment. And then okay, the next one, be careful. And then next one, we have a distributed load. Next one, we have to deal with the other external loading and force. Here we have a distributed load. Here we have distributed load. Okay, and how to represent distributed load? By a discontinuity function. Okay, here, okay, we just just use the value is 8. Sorry. Okay, 8. Okay, and then it start at the 0. Start at 0, and its power is 0. Okay, its power is 0. But this is not right. Okay, this is not the complete answer. Okay, because if I use the 8 bracket x minus 0 to the power 0, that means the distributed load is all the way from the 0 to the end of this cantilever. Okay, because right now we the range for distributed load only from 0 to 5. Okay, so we have to, so it's not distributed load all the way to the end of this cantilever. So we need to minus x. We need to minus another discontinued function at 5 power 0, and this is the distributed load. Okay, and next one is the moment, localized moment. Here is 50, and the moment with position at position equal to 5. Okay, and the localized moment, its power is minus 2. Okay, so and here is be very careful. Okay, be very careful. It's clockwise. So it's clockwise. So it's minus 50. Okay, but right now we want the internal moment. Okay, so we have to add another negative sign in front of the minus 50. Okay, so the overall is plus 50 bracket x minus 5, okay, to the power minus 2. Okay, so here I should mention this. Okay, no problem. Okay, sorry, never mind. Okay, so the final one, what's the final one? The final one is the localized loading at the end. Okay, what's the localized or concentrated loading? Okay, it's point down, so it's negative, and x minus which power should be I should shrink it. Okay, the power is at position equal 9, and its power should be minus 1. Power should be minus 1. Okay, but as we mentioned it before, if the load at the very end of the member, the load or moment loading, the load or moment at the very end of this member, yeah, we can ignore it. Okay, and the reason I explained it in the previous slide or previous sections. Okay, so and this is the very end, so we ignore it. Okay, so it's 0. Okay, so let us write down the complete. Okay, it's kind of messy. Okay, let's write down the final answer. The final answer is Final answer is 52. X minus 0 minus 1 minus 2, 5, 8. X minus 0 minus 2 plus 8. X minus 0, 0 minus x. X minus 5, 0. And here is plus 50 x minus 5 to the power minus 2. Okay, so this is our final answer. Let me check. Sorry, I made a mistake. I made a mistake here. Okay, well, what mistake I made? Okay, because distributed load. The distributed load here is point down. Okay, so this 2a should be minus a. So okay, you see. Okay, this is minus a. This is minus a. So okay, so be careful, minus a. So here is minus a. Here is minus a. So overall is will become it will become minus a plus 8. Okay. Okay, and then any other issues? Okay, let me check. Okay, so here's the loading function. Okay, yeah, be careful for the sign. Yeah, it's very annoying. Okay, so after we obtain this loading function, and we have to integrate it twice, or integrate twice to get the moment function. So let's do the integration in this video. I think this video I cannot show the complete process, maybe just half the process, and we will complete the calculation process in another video. Okay, so the integrated ones, we will get the shear force function. Let's call it capital Vx. Okay, just do the integration of the loading function. Okay, so the first one, this discontinuity function here, the power is minus 1. So how to do the integration function? How to integrate this? Okay, so just add the power, add 1 to the power, right? Because the power is minus 1, so it will become 52. It's a rule, right? Okay, this is 0. Okay, 2 by 8 is x minus 1. Just add 1 to the power, right? Okay. Okay, here for this one, this is not just only you can say it's only just if your power is 0.12, just use your the integration rule you learn in calculus. Okay, so it will become minus a x minus 0 power 1 plus a x minus 5 power 1. And here, once again, the power is minus 2. Just add 1 to the power. Add 1 to the power. Sorry. Minus 1. Okay, let's integrate once, but we have to integrate twice. So keep doing integration, and we have get a moment function. Okay, the first one, power is 0. Okay, just use the integration rule you learn from the calculus. So it's become like this, right? Okay, here the power, the power is minus 1. The power is minus 1. Just add 1 to the power, right? So here's 0. Okay, in this bracket, okay, the power is 1. Okay, use the integration rule you learn from calculus. So it will become minus 4. Power 2 plus 4 x minus 5 power 2. And next one, the final one, the power is minus 1. So just add 1 to the power, right? 50x minus 5, 0. Okay. And okay, let's check the unit. Okay, the first, the loading function. What's the unit for loading function? Its unit is kilonewton per meter. Yeah, I remember right. Okay. And the integration once the unit will become kilonewton. Okay, integration further, the unit will become kilonewton times meter. Okay, don't forget the unit. The unit, yeah. It's kind of very important. It's very important when you do some the final analysis. Okay, here we just start the video here because I have another half calculation process, but I don't want to make the video too long. Okay, here, okay, let's show the process. Let's review, kind of review the process. Okay, first of all, when you have apply a load on the beam, okay, you first of all use the rigid body equilibrium to calculate the reaction force and reaction moment, and then you have a complete the loading and moment acting on this beam. Okay, and then after you get this information, okay, write down or represent this moment and loading by a discontinuity function. Okay, but the moment you have to be careful. We want the internal moment, so we have to use the minus sign in front of the moment. Okay, because we want the internal moment, and be careful. And be careful for this the force direction. Be careful for the force direction. Okay, and after you get the intensity function, and then you have to integrate it twice to get the moment function. And when you do the integration, don't forget the integration rule for the discontinuity function. If the power of the discontinuity function is -2 and -1, just add 1 to the power. If the power for the discontinuity function is 0, 1, 2, 3, just use the rule you learn in calculus. Okay, so I just stop the video here, and I will show the remaining step for the next video. Okay, see you. Bye bye.